Hey guys, what's up? Eddie Alho here with KissAnalog.com. Oh, don't mind, don't mind that beast. That's for another video. Hey, I want to go over the selection of a few more parts on our PFC converter. These videos, I hope, will help those who want to go back and just look at, the selection of certain kind of parts. What I'll do after this, I think after this video, I'll run through the design and just select all the parts and stuff, okay? But I don't want to get into a lot of explanation. That'd be a very long video. So yeah, I'm kind of doing this way. Let me know what you guys think in the comments. So what I wanted to show you is how to select this diode, and the bridge rectifier over on the front end, okay? And I'm going to show you some more schematics here in a moment. So this is our boost diode. That one we have to have. This one's a bonus diode. This one helps fill this capacitor quickly when we first turn on the power. So that way the boost converter doesn't have to charge us up from zero, okay? Because he's going to be limited on current and how much energy he can put into each pulse. And this just kind of helps, fill up the tank. So let's jump in this video. Okay guys, here is our PFC boost converter, all right? Here's our EMI filter on the front end. Okay, we have our combo choke right here. We have an X cap here. We have an X cap here. These are safety caps. We call them X because they're across the lines. I did a video on this, but there's Y caps here. So that's our EMI filter, okay? And then our input protection is this fuse right here. And we have voltage protection with this MOV. I'm going to have to do a whole video on this stuff here, but yeah, we're probably not going to do, we won't do this. So anyway, I'll talk about that in another video. Okay, then we have a resistor right here will help limit inrush current a little bit. So when it first turns on, this guy right here will help limit the current that's racing in here to go up here, go around this diode and charge up this cap. Now the inductor will slow it down a little bit, but eventually the inductor will break down and will charge it this way too. If the boost converter never starts, that's what happens. And if the boost converter has a problem and doesn't want to start, the one way you'll know is this guy the voltage right here will just be equal to the peak of whatever the RMS voltage is at the input over here, okay? And that voltage can be anywhere from 85 volts to 265. This will give us that universal input voltage that the PFCs like to use. They have no problem. That's why we charge it to 400. And then we'll have a second converter with isolation and dropping the voltage down to the levels we want, okay? So that's all that stuff here. Let me get rid of all this stuff I put here. All right, so we have a bulk capacitor right here, this 270 microfarad cap, okay? When we first apply power, we're gonna get current come through the rectifier and through this diode right here. These are the main things charging out that cap initially. This resistor right here is it's monitoring how much current is coming through here. So during that initial current spike, current's coming this way and then going back this way, right? So when it does, it goes through that resistor right here, and this senses it right here. The current senses right here, okay? And that senses, it's trying to protect this FET. So when it's switching, it never, tries to handle too much current. It doesn't want to fully charge that real fast. It'll have a soft start. It'll take a little while to charge that up. So to speed that up, we use this diode right here. Okay, so that's what that function is. Okay, let me get rid of all this stuff. All right, so the bridge rectifier right here, let's choose the voltage for that. Well, we got to handle this large swing right here, okay? So when these diodes are reverse voltage. You know, we've got to make sure they can handle the current, plus we've got to make sure they can handle the reverse voltage. So we're going to use this as an example, this 300 watt eval card. Okay, so we have 300 watts in this design. This is just a example. This is the eval card I have. Okay, that's 300 watts. So the current in through here, worst case is when it's down to 85 volts, it can, you know, put out, you know, 4 or 5 amps, right? So that it can power 300 watts out here. We're going to have some losses in here too. Now at 264, it only has to put out just over an amp. So the current's going to be based on the low input. 85 is when our 120 volts drops down. We're going to say it could drop down to 85 volts before we stop running. Okay, so we have a large input voltage range. At the max voltage is when we want to choose this voltage here for this rectifier. So the max, when one of these diodes, it's providing this pulsating DC over here, right? So one side of the diode could be, on this side, it's going to have AC. So one side of the diode could be at the negative pulse, and the other side of the diode could have a positive pulse. So it's peak to peak. So we want to have, you know, we want to have some voltage protection here. We want to have probably 600 minimum, maybe up to 800. So we're going to look up this part number and see what they chose for this. All right, so they have this on semi part in here, okay? And we're going to come down and take a look. Now they chose the 8J. They chose this one right. They chose this part right here, this 8J, okay? So let's come down here and take a look. Now, first of all, the current looks like it can handle the peak currents big time, 200 amps peak. That's great. So let's come on down here. 8J, so that's a 600 volts. So that's kind of a minimum value. I'd actually feel better with the 800 volt. So I'd probably choose an 800, but 600, and you know what? You could even choose 1,000 if you find them, but 600 minimum. Okay, that's what they chose. I would say probably go 800. Now, forward current's 8 amps. That looks good. That's when it's 100 C, so that's when it's running hot. So that's probably good. Now, the other thing to look at is how many degrees C per watt. How hot does it get? Junction to ambient. So right here, this at 18 degrees C per watt. So if it's dropping, you know, 1 volt, says 1 volt forward voltage drop right here. So we'll have 1 volt on 2 different diodes at the same time, and then the other 2 diodes will have 1 volt. So at all times we'll always have 2 volt drop. And so if we say our average currents, say, you know, low line is 5 amps, then we would have 10 watts. So, you know, that's going to get pretty hard. That's 180 degrees, you know, with this junction ambient. So we need to heat sink that, okay? Now this note here says it is heat sunk with this. So that's the kind of math we're going to walk through and look at to see if, you know, how much current we actually have. But those are the things we're looking for, okay? Just kind of walking you through, kind of showing you this, and then I'm going to do a design example in another video. Okay, the curve on the right has right here VF forward voltage, and it's plotted against IF forward current. So it shows you that, let's say, for instance, 10 amps, come down here, 1 volt drop. Okay, so if it's 5 amps, it's going to be a little bit less. So that's how you use this curve. But the other part about this I want to point out is it doesn't have different curves for the different voltage ratings. So that means that you could select the higher voltage rating and still have the same thermal performance. So when you choose one of these guys, you know, these might be a little bit more expensive, but since we don't care, since we're only building a few or one, or, you know, for yourself, then you may not care if you spend another 10 cents. All right, guys, so we're back here. So let's get rid of all this stuff. Okay, now Now let's choose this diode. Again, this diode right here, this is the one that's charging his cap when we first turn on, okay? So let's see what value they chose. Now we want to handle that current, that first initial inrush current. Then after that, he's going to kind of go to rest, because once this converter kicks on, he's going to boost this voltage up 400, and this guy won't be working anymore because he's going to be turned off, okay? Because the voltage on this side will only be as high as the peaks of these, and this would be 400, so this should be always higher than the anode, so he'll turn off. So we want to make sure when he's off, you know, that he's going to be okay. So what's the lowest voltage on the anode side? Well, since it's pulsating DC over here, it never goes below 0. So 0 would be the lowest right here, 0 volts, okay? So on this side, the cathode, he's going to be regulated at 400. So he's going to have 400 volts across him whenever this guy's down at 0, okay? And when he's up at the top, he's going to have less. So, you know, 400 volts is all we need. So let's go look at this part number and see what we have. All right, guys, this is the one on semiconductor. So this used to be Motorola, by the way. 1N5400 through 1N5408. Now they chose 15406. Let's go down and take a look at it. Okay, here we go. Here's the tables right here. 600 volt. So that's about a 70% derate. So that's, I mean, we're only using about 70% of that 600 volts. So that's great. We got, you know, some margin. So now again, we could go with 800 if the cost is negligible, because, well, let's look at the curves down here. Now here's the junction ambient temperature, 53 degrees C per watt. So you can't handle a lot of power, okay? Now it says 3 amps rated, and that's at 105 degrees, okay? For peak currents, let's take a, okay, so right here it says 1 cycle 200 amps. That's crazy. That's very good. Forward voltage drop is 1 volt. So we're not worried about power drop on this so much. Let's come down and take a look. Okay, right here on this right curve, number of cycles. So if we only have 1 cycle, it could go to 200 amps. See, on the left side, it's current. Now, if it takes several cycles before the PFC kicks on and turns it off, maybe 10 cycles, we can go to 90 to 100 amps, okay, for 10 cycles. So that's pretty good. So we just want to limit the inrush to 200 amps for sure. Now in the left curve over here, let me come down here to the bottom, instantaneous voltage. So the voltage across it, the current through the voltage, you know, current multiplied by the voltage would tell how much power is across it, right? Now, if it's only, say, 10 amps, it's only about 0.9 volts. And so if it comes up, say, 100 amps, you come down here, it's like up to 2 volts. Again, we won't care if it's only a few pulses, right? Yeah, so that's how this guy was selected. And, you know, you can see the package. These are both through-hole parts. You know, it's an eval card, so through-hole parts are easier to evaluate because you can, you know, they're just easier to replace if you damage, and, you know, and they're probably inexpensive, and just, yeah, so they just did it because you can also put scope probes on the leads easy and stuff like that. All right, guys, so let's get rid of some of this stuff here. And let's look at this diode. Okay, how was that diode chosen? Well, similar to the one up above it, it's going to have 400 volts over here. So 400 volts on the cathode. On the anode, he's going to be pulled down to ground through this transistor. So that's the lowest he'll go. He won't go negative. So the most he could ever have is 400 volts on him. Okay, so yeah, so there you go. Same thing as this guy up here. So probably a 600 volt diode. So there's the part number right there. It's a 4068, the last part. So let's go look at that one. Oh, and as far as current goes, so this is 390 volts. Okay, so at 390 volts, he's not supplying very much current. Say at well, let's say if it's 390 watts, he'd be supplying 1 amp average out here. So yeah, so this guy, current wise, 1 amp is good. We've got to make sure he can handle 400 volts. So let's go take a look. Now, here's the special thing about this. I'm going to show you some TI notes here in a moment, but see this? This is Schottky, this symbol. And Schottky diodes, you normally don't find them in high voltage like this. So I'm going to show you why that can be so in this case. But what's so great about Schottky is this diode above, when it turns off, it takes a moment for the electrons and everything to kind of settle out in the PN junction. And so meanwhile, there's a little bit of leakage current that goes through this diode, okay? So on a converter like what we're doing, where we're having continuous current going through here, so this guy's on during the whole time he's forward biased, and where, like, let's say if it's discontinuous, this inductor would go dry, he would run out of current, and so the voltage on this side would just naturally sag to zero, right? Essentially. So it would drop. There'd be no current flowing. So the electrons and the mobility carriers, all the things that go on inside the junction would all settle down, and it would look like a perfect diode. So when the voltage up here on this side, it would be blocked. There'd be no current flow through here. Okay, so once that happens, but during that time, during that exchange where everything's settling down, there is a little bit of energy going through here, and there's voltage across it, and so there is a power loss. But with the Schottky, there is no reverse current. It doesn't go through the same problem that a PN junction diode does. Okay, silicon carbide, even though it's silicon carbide, it's still a Schottky diode. It has a Schottky behavior versus a basic rectifier. So rectifiers have that little bit of leakage when they turn off, okay? And same with your bridge rectifier here. There's a little bit of leakage every time they turn off. They're commutating and they're on, off, but they don't turn off instantly, okay? But it's slow enough over here, it's not a problem. Over here, this guy's switching. So over here, the reverse current is actually meaningful. It actually can double the amount of power you lose on your diode. So that's very important. So let me show you this diode first, and then we're going to show you some notes. All right, so here's the diode. Now this was made by Wolfspeed. They were a leader, or are a leader, in silicon carbide Schottky diodes. Okay, they came out with some of the first ones, kind of like GaN FETs. Schottky, or the silicon carbide, made a big splash in the power industry, just like GaN did. So between GaN and silicon carbide, they're really changing the power industry. Okay, so this one's rated for 600 volts. Again, that's perfect. That's plenty. That gives us 70% D rate on this 600 volts. And 4 amps, that sounds like plenty too, right? So let's take a look down here. See right here? Here's the feature right here. Look at this. It says optimized for PFC boost diode application. Zero reverse recovery current. So this guy right here saves a lot of power dissipation. That's huge. That improves your efficiency and keeps this diode from having to be gigantic. Okay, applications over here on the right side again, switching power supplies, PFC converters, solar inverters, AC DC converters. So, oh, and by the way, on the features down here at the bottom, extremely fast switching. So like a GaN FET, it's kind of like, you know, the GaN FET advantages. Okay, so here's some of the information down here talking about how much current can do repetitively and all that kind of stuff. So yeah, I mean, this looks like a great diode. But now this power dissipation thing right here, this is the big consideration, because since, you know, it's sending current across, now if it's, we got to look at the forward voltage drop, and let's say if we have an amp, how hot are we going to get, right? So we want to make sure that it says we can go 13 watts with 110C. That's pretty amazing. Now, here's the capacitance stored energy. So this is the stored energy when it's switching. This is how we just have so little energy, 1.4 microjoules Up here, the total capacitive charge, QC, 10 nanocoulombs. So that's just really small stuff, guys. The forward voltage drop, depending on the temperature, see, once it starts getting hot, it's going to be somewhere in between these things. So let's say 1.7 might be a good place to start. And could, you know, so you can come down here and look at curves and things like that. But here's the temperature. It goes up almost 5 degrees C per watt. Okay, so that's why you don't want to dissipate too much wattage, because these things will get hot. Okay, curve on the left is forward voltage drop, and on the vertical axis it's forward current, and you can see at different temperatures. Now you can also see right around in here at 2 amps, let's say, you're about 1.5. But if you're closer to 1 amp, then you're getting, you know, you're down here just barely over 1 volt forward drop. So it's getting pretty close to 1 volt forward drop. That's a great diode. Okay, guys, this is the TI app note, and they talk about how to do the math and all that stuff, and, you know, how to consider the parts and how much just, they show you how to calculate the power drop and all this kind of stuff. And this is a bridge rectifier, and they talk about 1 volt across the rectifiers, and they kind of show the math here. So they're showing you the math here, okay? And they're saying a heat sink would be required to maintain operation, you know, so in a safe operating area. All right, guys, and this is the boost diode, okay? So forward voltage drop, you know, they're talking about 125C reverse, the reverse recovery charge, QRR of the diode is important. Using a silicon carbide Schottky diode, although more expensive, will eventually eliminate the reverse recovery losses. Okay, so here's an important feature right here. Using the silicon carbide Schottky diode, although more expensive, will essentially eliminate reverse recovery loss and result in less power dissipation. And that, even though the diode itself is going to cost more, your heat sinking is going to cost less. Okay, so here you go. Here's the math right here. The QRR, like QRR 0 nanocoulombs, I mean, it's so little that it's negligible. May not be 0, but it's close to it. Now the other diode, they don't really talk about, because they figured that you could probably figure that out yourself. Hey guys, so what do you think? Was that helpful? We're going to jump into the next video where I think we're going to go through, I'm trying to decide. We'll see. I might do one more video just on the FET alone, but I may just jump into it and do the whole thing, and we'll build up the schematic, okay? Yeah, I have to think about that. Let me know what you guys think. 2 thumbs up to my patrons, and 2 thumbs up to the members of the channel, and a big thumbs up, an extra thumbs up to Danny, the team member of, you know, my YouTube channel. So, hey, I got one. That's awesome. So, and a big thumbs up for those who have, I think there's one guy who bought me a beer, or I think he bought me a 6-pack. So appreciate it. Thanks a lot. Put his name down here. That's awesome. Appreciate the support. These videos get a lot less views. They get a lot less subscribers for some reason. A lot of people that watch these design videos just don't subscribe, but they watch them all. And, you know, I mean, typically on my channel, it's funny because 70% of people don't subscribe, even though they watch a lot of videos. So people just don't subscribe. On these design videos, it's even fewer. And yeah, so, but I still want to do them. And so really appreciate the like, the comments, and subscribing if you haven't done so. If you think you have, just check down below. It says subscribe. For some reason, YouTube, I've unsubscribed you. And there's a super thank you button down there too. Appreciate that. Buy me a beer, buy me a coffee, something. Or just like the video. That's all you really need to do. Thanks for watching, and we'll see you next time.